Hello everyone. So we will move on to discuss momentum and kinetion in this lecture video. So first let's introduce the concept of momentum. The definition is quite simple. Momentum using the symbol P and we put an arrow on top, which means is a vector, is defined as mass object times the velocity of its object. Mass is a scalar, and velocity and momentum are vectors. So momentum has the same direction as velocity. Now if we analyze the unit for momentum, is mass times velocity, so its unit should be kilogram times meter per second. Now since the momentum, just like a velocity, is a vector, so it has components. So if we have something moving in two dimensions, it will has component in x direction. Px equals mass times velocity in x direction. Py equals mass times velocity in y direction. This is different than the concept we just learned, kinetic energy. Kinetic energy is a scalar, is p squared divided by 2m. Now p squared, it gives a scalar. So kinetic energy equals 1/2 mv squared, also equals p squared over 2m. So momentum and kinetic energy is in a sense related. For the same object, larger momentum basically means larger kinetic energy. Now let's introduce the concept impulse. We start with Newton's second law, F equals ma, and we also know acceleration is change of velocity over time. So change of momentum divided by time gives us force. This is Newton's second law. Actually, this is exactly what first proposed by Newton in his book. Force equals change of momentum over change of time. So we have change of momentum divided by time give us force as well. Now we want to do something. We start with change of momentum divided by time give us net force. We can multiply a time on both sides. We can multiply time on both sides, then we have force times time. Force times time, and then we define this quantity, force times time, impulse. And we can see impulse is also a vector. It has direction. It has exactly the same direction as the force. Its unit is kilogram meter per second, because the unit for force is kilogram meter per second squared. Then we multiply by a time which has unit second, so it becomes kilogram meter per second. And this will also have the same unit as mass times velocity. So, which is not surprising, because starting from left-hand side and the right-hand side, say if you multiply delta t on both sides, left-hand side would become delta p. Change of momentum delta p would equals to force times delta t. Change of momentum equals force times delta t equals impulse. So we arrive at a very important conclusion. The impulse of the force acting on the object equals to its change in momentum, and we call this one impulse momentum theory. Impulse momentum theory. So the net force acting on object, the impulse of this force would equals to the change of momentum of the object. Impulse equals change of momentum. We call this one impulse momentum theory. And because impulse equals force times time, so if we have a change in force, If we do the same analysis, we would find out that the area under this force versus t plot will give us impulse. So area of this shape will give us impulse. Now we want to define an average force. This force is changing from Ti to Tf, right? We want to define a constant force acting on the object from Ti to Tf, but the impulse given by this constant force would be exactly equal to the impulse given by this changing force. So we call this one an average force for this changing force over the time period from Ti to Tf. So why do we need that? Is that if we know the change of momentum, then we can estimate what would be the average force acting on the object. So we can calculate the average force as change of momentum divided by delta t. So we can do an example to try to understand that. So the ring come down with velocity negative 15 meters per second, hit the roof of car. Now when the ring dropped to the roof of the car, the ring would stop on the top of the roof, so velocity becomes 0, right? And the initial velocity negative 15 meters per second. So apparently we're going to choose positive to be pointing up. So the ring going down, so the velocity of the ring is negative 15 meters per second. So let's roughly estimate the mass of the raindrop is 0.06 kilogram per second. Just how many rain dropped on the roof of the car. So in 1 second, there is 0.06 kilogram rain dropped on the roof of the car. And we want to find out what's the average force exerted by the rain on the roof. So we can find out the change of momentum of the rain in 1 second, right? In 1 second, there is 0.06 kilogram rain dropping on the car, so we can calculate what's the initial momentum of the rain, what's the final momentum of the rain, so we can find out what's the change of momentum in 1 second. And after we find this one out, in 1 second we can estimate what's the average force. And that's exactly what we are going to do. So the force would be change of momentum divided by delta t. Now final momentum is 0, so this one is 0. So we only have this term. We're going to divide delta t on both sides. So it's negative mv0 divided by delta t, and v0 independent of delta t. M divided by delta t is given. M divided by delta t is 0.06 kilogram per second. Initial velocity negative 15. So the force is 0.9 Newton on the roof of the car in this program. So now let's think what's going to be the difference if we have the rain and the hailstones. So the difference between hailstones and the rain. For the raindrop was stopped on the top of the roof, right? So change of momentum would be simply mv0. Okay. Now if it is hailstones, so first try to think the force on the roof, is it going to be larger than the rain or smaller than the rain? From our common sense, hailstones sometimes could destroy, not destroy, but damage the top of the roof of the car, right? So common sense tells us the force from a hailstone should be larger. And why is that? Because hailstone were bouncing back. So for the hailstone, change of momentum is given by final velocity and final velocity subtract, and the final velocity is positive. Final velocity is positive, and initial velocity is negative. So let's use the example we have. If V0 is negative 15, so this is just the mass times negative 15. That's change of momentum. You have a negative sign here. So if this is for raindrop, so this is for rain. This is for raindrop. This is 0. So change of momentum is just 15 times m. Now let's see we have hailstones. This is negative 15 meter per second. But let's say in final velocity is 10 meter per second, and it's pointing up, so it's positive 10. So this is going to be m times 10 subtract the negative 15, right? Subtract negative 15, because the initial velocity of the hailstone is pointing down, so it's negative 15. Final velocity is subtract, and this is going to give us 25 m. So the force, so for the same initial velocity of hailstone, same mass, the force from hailstone is going to be larger than the force from the rain, because the rain just has a smaller change of momentum. And hailstone has larger change of momentum because hailstone is going to bounce them back. Okay, now can we try to think? This is fairly high, and if we jump from here to the water, we are relatively safe. If it's not water, then nobody should do that, right? And if it's water, why is relatively safe? So another scenario, if we throw something from the same height to a concrete, let's say concrete. From kinematic analysis, the velocity of the object here would be the same because it's coming from the same height, right? And then eventually the object is come to a complete stop, from V to complete stop. So change of momentum should be the same for water and for harder concrete surface. But how about the time of contacting? After we get into the water, how long it takes for us to come to a full stop, or object go to a harder surface, come to a full stop? The time here is much larger, right? Time here is much larger. Let's just delta t1, this is delta t2. So delta t1 is much larger compared to delta t2. Then how do we estimate average force? Average force equals to delta p over delta t1, and delta p is the same, right? So let's call this one average force 1. This is average force 2. Delta p divided by delta t2. Okay. So from our analysis, from the instant object enter the water to come to a complete stop, change of momentum is the same from here compared to this scenario, harder surface. The time it takes for the object to come to a full stop is much larger in this scenario and smaller in this scenario. So delta p the same, delta t1 is much larger than delta t2. Then how does average force compare? So if delta t1 is much larger than delta t2, we can conclude force here is much smaller, right? So This one is small, and this one is not. And this is why we can do cliff jump, because the water acting as a buffer, it will increase the time for us enter the water to come to a complete stop. The water increases the amount of time during which the momentum is changing, and they reduce the average force. That's why cliff jump is relatively safe. It's not absolutely safe, but relatively safe because of impulse momentum theory.